Hello again and welcome. I guess it's been a couple of months since we've made a video. Today I'd like to talk about using the NanoVNA to measure a power distribution network. So what is a power distribution network? It's basically what it sounds like. It's everything between the power supply and the devices. You can see this is all on a wire wrap board. There's a couple of FPGAs here. I've done wire wrap boards all the way up to 100 megahertz. The transition rates of the logic that we use today is much faster than what I'm showing here. Here's some bypass capacitors. You can see it's using a combination of tantalums and ceramics. So if we look at the larger FPGA, you can see there's different values being used. The FPGA and memory devices used on this particular board are all 5-volt logic. On modern FPGAs, the core voltages are much lower. So today, to properly design a PDN, it requires a little bit more thought. There's several good videos and papers that cover PDN design and measurement. In this video, I'd like to focus on how to use the new features that I've added to my software to make these measurements. So first off, you notice I have 3 different network analyzers. This is the original NanoVNA that Flipper bought me. And then here we have the V2 Plus 4. And here is a new one that I bought. This is the H4. So in order to measure a PDN, we'll need a network analyzer that can operate at very low frequencies. You may wonder, if we're talking about high-speed digital designs, why do I care about low frequencies? Typically your power supply is going to be located on the same circuit board with your logic, and the loop response of those power supplies is going to be very slow. So what we'd like is a network analyzer that can make measurements well below a megahertz. Another problem that you run into is the inductance of a lot of components is going to go up at higher frequencies. So if we're trying to measure low impedance, we may have to do that at lower frequencies. We'd also like a network analyzer with very low noise and also a very wide dynamic range. And the reason for that is typically with a PDN, we're trying to measure very low impedances. Most of your PDNs are not going to be 50 ohms. And of course, for a high-speed digital design, we'd also like to look at high frequency. Our circuit board may only have a clock rate of even 10 megahertz, but typically for EMI, we have to test well above a gigahertz. So it's very possible that the designer is interested in making measurements well above the clock rate of the board that they're testing. So if we look at the V2 Plus 4, this has a lower operating frequency of 50 kilohertz, and it only has a 10 kilohertz resolution. That's not a very good resolution, and 50 kilohertz I would say is marginal as far as the low frequency that we're interested in looking at. Some of the problems that I ran into initially with the firmware for the NanoVNA still exist on the latest firmware for this H4. And unfortunately, I don't see that firmware getting fixed. If you want the 401 data points, then I would say try some of the other firmware that's available. But if you want to try to use this with my software, I would say don't waste your time, because what I find is that the thing can actually output random glitches. And again, that's not a problem with my software, it's a problem with the firmware in this, and it's a problem that's been solved with the original Nano, well over 2 years ago. There's a person who's working on a new open source VNA. It's called the EEVBlog. Again, it's supposed to be low cost. That particular VNA has an upper frequency limit of 6 gigahertz compared to 4.4 on the V2 Plus. The downside is it only has a 60 dB dynamic range below 1 megahertz. And another major problem with it is its lower frequency is limited to 100 kilohertz. And again, that's not going to be acceptable for making PDN measurements. I have a few other VNAs beyond these low-cost instruments. One of them is an old 8754A that was manufactured by Hewlett-Packard back in the 1970s. My particular version of that VNA has an upper frequency limit of 2.6 gigahertz. Unfortunately, the lower end is limited to 4 megahertz, and if you want to do any kind of narrowband measurement, you have to hook up an RF generator and control that separately, so it's a real pain to use. I also own a HP 3589A. That's a little newer network analyzer. It's kind of an oddball in that it's actually a network analyzer as well as a spectrum analyzer. It can do vector network measurement, but in order to do that, you have to attach an external directional coupler. That particular VNA is good all the way down to 10 Hertz. That would be ideal to measure these PDNs. Unfortunately, the upper limit of it is 150 megahertz. So again, not a real good solution. I also own a newer Agilent VNA. It actually has a pretty good noise floor and the dynamic range is really good on it. The problem with that network analyzer is the lower end is limited to 300 kilohertz. Again, that's far too high to be used to make these measurements. On the high end though, those network analyzers will run all the way up to 3, 6, or 9 gigahertz, so that's well above what we would need to measure our PDNs. So unfortunately, out of all the network analyzers I own, none of those are really suited for making these measurements. So we're going to attempt to make these measurements using the original NanoVNA. The firmware that's installed in this particular unit is good for 10 kilohertz on the low end. Again though, with this hardware, once you get below about 20 kilohertz, the noise starts to go up. So 20 kilohertz is probably about the lower limit of it. This is looking at the latest software that I've released up on GitHub for the original NanoVNA. You can see this is version 1.08. Currently I just have a through attached to the Nano. Let's go ahead and we'll select 2-port cal. We'll select old in calibration, and now we're going to select the 10 kilohertz to 10 megahertz single port SOLT cal, and we can see that the unit is now calibrated. First thing I'd like to point out with the older software, notice towards the bottom of cursor A and cursor B we have these separate readouts in green. These were added for series transmission measurements. And for these PDN measurements, we're interested in looking at the shunt impedance. And of course, the main problem with adding more readouts, first of all, it's getting confusing. Second of all, we're out of room. So you either have to make the display larger, which I'm reluctant to do because with the application the size that it currently is, I'm able to run it on my tablet as well as my laptop without an external monitor attached. If I were to select transmission rectangular, again we can see we're sweeping between 10 kilohertz and 10 megahertz. Let's go ahead and select a center frequency of 10 megahertz. You can see the center frequency changes, but the span does not change. So this was a minor inconvenience with the older software. So let's go ahead and select a 2 megahertz span, and now you can see we're sweeping between 9 megahertz and 11 megahertz. And we can see that reflected on the display. You can see a center frequency of 10 megahertz with our 2 megahertz span. The problem with this is if I want to go back to sweeping between, say, 10 kilohertz and 10 megahertz, if I select the 10 kilohertz start, you can see it's again sweeping between 10 kilohertz and 11 megahertz. The new software will work a little different. Basically, you only need to select one or the other, and it'll automatically update the start and the stop, or the center and the span. Again, I just did this for my own convenience. So let me go ahead and we'll fire up the new software. Again, we'll go ahead and select the defaults, and we can select link, and we'll select sweep. Let's go ahead and we'll load up the 2-port cal. Again, we'll select old, calibration, and we'll use the 10 kilohertz to 10 megahertz again. You'll notice that I've removed the transmission readouts for both cursors. I've also moved the model up to this area here, and off to the left of this you can see I've created this new widget for the measurement type. So currently it's selecting the shunt measurement. If I select transmission, for example, this will go over to series measurement. We can also change this manually back to shunt or to shunt through. So now when series is selected, the RLC measurements will change to reflect that. And now what I'd like to do is change our center frequency to 10 megahertz again. You can see instead of having the center frequency in the span, it's showing a start and a stop frequency. So what I've done with this new software is I've simplified it to work more like the V2 Plus, in that I always set a start and a stop frequency. So when you're changing the span or the center frequency, I always calculate a new start and stop. So with the older software, I always use the frequency command to determine what frequency each point was at. And I no longer do that because, again, with the V2 Plus, I end up having to calculate all those frequencies anyway. So this software now for the Nano works the same way. Now again, with some firmware running on the H4, you have the ability to run above 101 data points. So the way that the software works now, you can actually change the number of data points. You see it's programmable, and you can save this into the default file. So the next time you run the application, for example, if you've set this to 401 data points, the software is expecting that the Nano has 401 data points. Now if I wanted to go back to a start and stop frequency of 10 kilohertz to 300 megahertz, I just select one or the other, and you can see it changes both the start and the stop. Again, it's just more convenient for me to run it this way. Let's change this back to 10 megahertz. Let's go ahead and install our T-check. And again, this T-check is used with my transfer relay to check the calibration. And again, this is nothing more than two 100 ohm resistors in parallel to ground. So let's go ahead and we'll attach this just to port 1. And let's select our shunt measurement. And you can see it's measuring 50 ohms. Now let's go ahead and we'll connect port 2. And again, this is a 50 ohm input. So we now have two 50 ohm resistors in parallel, which is going to be 25 ohms, which is what we're displaying. So now let's do the shunt through method. And you can see we're reading roughly 50 ohms again, so 51.6. Right, so here I have a breadboard. I'm sure a lot of you have one of these at your disposal. This is going to simulate our PDN circuit. So without anything attached to our breadboard, you can see if I go from shunt through, which is currently reading 72 ohms, and we go to shunt, you can see it's reading 50 ohms, and again, that's because port 2 is indeed 50 ohms. Now let's try it at series. You can see it's measuring roughly a half an ohm between the two. Let's go back to shunt, and here we have a 50 ohm resistor. I'm going to apply this from ground to our VCC, and we can see we're reading roughly 25.2 ohms. And let's go to shunt through, and you can see it's reading roughly 50.8 ohms. That's what we'd expect for our 50 ohm resistor. Let's go ahead and we'll place that with a 47 nanofarad capacitor. Looking at our software, there's our resonant point at roughly 3.5 megahertz. In this area, where the trend is downwards, it's acting like a capacitor, and in this area over here, it's acting like an inductor. Let's put a 10 ohm resistor in series with it. And now we can see our capacitor's ESR is measuring roughly 10.4 ohms or so. Let's replace our capacitor. This is a 100 microhenry choke. Again, we'll just go from VCC to ground, and you can see we're reading roughly 100 microhenries. Typically the impedance of a PDN isn't going to be 50 ohms or 10 ohms. This is one of the standards I made up for a previous video. This is a 100 milliohm resistor. It's 1%. What I'm going to do is just attach this between port 1 and port 2. You can see for cursor A we're reading roughly 105 milliohms versus 106 for B. See right here at about a megahertz how the signal starts to take off. This is where this arrangement becomes inductive. Now again, we've calibrated using this set of standards, which is the same material as this circuit board, the same style connectors. So we basically nulled out all the errors that these components cause. So what you're seeing here is the inductance of this particular package. So remember again, I was talking about our need to measure at lower frequencies than even a megahertz. And this is the reason I'm saying that we need a vector network analyzer that'll work at very low frequencies. So let me just talk a little bit about what the shunt through measurement is and why we would want to use it to measure the PDN. Why can't we just attach port 1 directly to the power plane of our device and measure the impedance that way? So if we look at the shunt through method, we're now going to use port 1 as well as port 2, and we're going to place our device between these two. For a series through measurement, we would place it between the two signal paths of port 1 and port 2 in this area here. For the shunt through method, we're going to place it across the signal path and the ground return. Why would we want to do this? It seems a lot more complex than just using our simple S11 measurement. I'm sure a few of you own some bench meters with a fairly high resolution, and it's quite common that those will have a 4-wire Kelvin feature. So basically, the 4-wire system, we have our device out here that we want to measure. We attach that to what we call the source, and that provides a current through our device. And then we have a high impedance voltmeter that attaches directly to the device. And the nice thing about this is where normally a multimeter is measuring back at these points here, and these would be your test leads. You have all the losses of the leads, the connection points back here, the connection points to the DUT that you have to deal with. So for low impedance measurements, that doesn't work very well. So using this technique, we can actually get a very accurate measurement. So looking at the shunt through measurement, you'll notice it's very similar. Here we have a source, it's port 1, and we have an input which is port 2. The problem that this configuration has is that when we look at the current flowing through our device, once it reaches this node, the current can either go this way or it's going to go this way. So when we look at a network analyzer like the Nano, and again, this isn't a problem that's unique to the Nano or these low-cost network analyzers. The basic problem is that the two ports share a common ground, so that's forming this ground loop. And of course, at very low frequencies, that's going to become an issue. What we need to do is find a way to break this ground path. So one way to do that is to add a common mode transformer. So again, we have port 1, and over here is our port 2. And now we're going to place this transformer between the device that we're testing and port 2. The idea with this transformer is this has a very good common mode attenuation at low frequencies. Typically what's going to happen is at higher frequencies, I'm talking like 10 megahertz and up, the coax cable is going to be so lossy that this isn't really going to be an issue. And I demonstrated that when I was looking at some very low ESR high Q RF parts from American Technical Ceramics in a video a while ago. That basically I didn't have to deal with the common modes because the coax cable itself was so lossy. Because this is a 50 ohm system, it's very important that this transformer be 50 ohms. We don't want there to be any kind of a mismatch. The other thing is we want very good common mode rejection at low frequencies. So common mode needs to be very good at less than 10 megahertz. We'd also like very low return loss at very high frequencies. Again, for PDN, we may be interested in looking at signals well above a gigahertz. So this transformer needs to have very low loss and be very flat over that entire operating range. Another problem when we're looking at the PDN is this is going to be a powered device. Most VNAs are not going to like you putting a DC source directly to their inputs. It's a good way to destroy one, so I wouldn't recommend you do that. What you need to do is somehow break the DC path, and we do that with something called a DC block. Of course, that is nothing more than a capacitor. So we're going to apply a capacitor on the source port as well as on the receive port. Now any DC that's present on the PDN is going to be blocked from getting into our network analyzer. Now one of the things I saw somebody post recently is they were saying basically a DC block is going to protect the network analyzer from connecting it to a DC source. Yeah, that's total bullshit. If somebody's telling you that, just walk away. So what can happen, right? A capacitor impedance for DC is, sure, it's very high. It doesn't pass DC, but it does pass AC, and the higher the frequency, the impedance is going to go down. So what ends up happening is we connect our network analyzer up with our DC blocks, and we think it's going to save it, and then we apply power to the PDN. So what ends up happening is if we're looking at the voltage with a scope or a meter or something, we're down at 0 volts, and all of a sudden we turn on our PDN, and let's say it goes to 12 volts or something. So the frequency content in this step here when we turn it on could be very high. That can blow right through these capacitors, right into our network analyzer, and take out the front end. So don't do that. At the same token, you don't want to discharge these very fast. So, let's say you've got 12 volts, it's all charged up, and then you short out the supply or something. Well, you got the same problem. You've got 12 volts on this side of the plate, you yank it to ground. This capacitor is going to want to stay at 12 volts across it, and that's going to yank the port down to negative 12 volts, and essentially, again, we blow out the network analyzer. So just be aware when you're playing around with this stuff, you can damage the network analyzer. Nice thing about this is, we're talking about a network analyzer, it costs $50, so it's not the end of the world. So let's talk about the DC block a little bit. Again, we said it's nothing more than a capacitor. These are a couple of homemade ones. You'll find that companies like Mini Circuits, for example, do offer DC blocks. The problem with those is that they're not going to be good for the low frequencies that we're interested in measuring with this PDN. We'd like this to be good to at least 10 kilohertz and up to whatever frequency we're interested in, say 1 gigahertz. So we want a very flat response across that entire operating range. Another thing that you want to be aware of is if you're using something like an X7R or Z5U, for example, the capacitance is going to be very unstable with the voltage that we apply across them. So again, just keeping in mind that that capacitance can change with the voltage across it. You have the same problem with the PDN itself, right? You've got a bunch of bypass capacitors. A lot of those are ceramic, and when you power up the PDN, the impedance is going to change versus having it off. So there's a few companies out there that offer DC blocks as well as common mode transformers. The problem is, for the hobbyist, they cost a fair amount of money. Even just one DC block is going to cost more than what your Nano probably costs. So what I chose to do is make all my parts. The one on the right is one of the first ones I made that actually performed well enough that I decided to go ahead and encase it. This unit's 3 dB point is at 2.4 gigahertz. Both of these transformers are made from a combination of different materials. You can see the common mode attenuation at 100 Hertz is 3.2 dB. At 10 kilohertz, it's all the way down to 25 dB. At 100 kilohertz, 37 dB. Again, these are both coaxial type. This one's using SMA, and our other one is using N connectors. Just give you an idea of the cost on these, just these connectors here alone, they're not the greatest quality, but these are $50 a piece. So there's two of them, there's $100 right there. Both these transformers utilize tape wound cores. Those are quite expensive, and those parts are the next highest cost of the whole transformer. This particular one cost about $200 in parts to make. This one's a little cheaper, but not by much. You'll also need some probes, and all I'm using here is 2 sections of coax. And you can see all I've done is I've cut the braid back a little bit, and I've taken some magnet wire and I've wrapped it around that braid and soldered it. And the idea with this is I can solder this directly to a bypass capacitor on a circuit board. This is the user's manual for the software. In section 23 I start going over the PDN measurements. Of course, we've covered a lot of this already, but there's a few things I'd like to go over in this document with you. So here I talk about one of the commercially available transformers. This one is produced by Picotest, and it's a part number J2102B. I had reached out to Steve Sandler at Picotest. I was trying to understand some of the graphs that they provide on their website that shows the performance of their transformer, and unfortunately I really wasn't able to get a straight answer from Steve as far as what it was exactly that those graphs were showing. But I ran into a gentleman named Brian Walker. He works for Copper Mountain Technologies, and he had one of these transformers available. He was kind enough to do some sweeps on one of their network analyzers, so he made all those S parameters available to the public. So I'd like to personally thank him for providing us that information. This is a photo that Brian provided us. This is him measuring the common mode performance of the Picotest transformer. Again, you can see he's got his Copper Mountain S5065 network analyzer, and he's got a couple of strip pieces of coax, and he's attaching to the outside shield of the transformer. So he's measuring S21 across the shielding of the transformer, and this is what I would have expected him to do. And of course, I'm sure that there's a few of you that are saying, oh, you know, this isn't going to be good for looking at 6 gigahertz, obviously, having this coax dangling out here. Again, that's not the point of this test. What we're interested in looking at is the low frequency common mode performance of the transformer. So in our case, something below 10 megahertz, for example, on down to whatever the range of the network analyzer is good for. And I believe that this particular network analyzer he's using was good down to 9 kilohertz. So here you can see I have a couple of BNC to N connectors. One of them is just essentially the center conductor feeding through to the center conductor of the N. In the one on the right, you can see it's connecting the shield of the N up to the center conductor, and in both cases the BNC's shield is unterminated. And again, these fixtures are just to look at the common mode performance of my own transformers. This is looking at measuring the common mode performance. Again, I'm using the HP3589A. Again, that network analyzer is good down to about 10 Hertz and up to 150 megahertz. So we cannot use that to look at the return loss, but it certainly does a very good job looking at the common mode performance. Here's showing a small stack of some of my cores. Off to the right, this is one of the very first transformers I made. I don't know how many cores are in here. It looks like maybe 6 total. And there's 2 different types of material being used. I'm not sure exactly what these were. Basically, what I was wanting to show here is that if you look at the different ferrite materials, they're going to have different frequency responses. So what I'm doing is I'm combining different materials to give me a wider range of common mode rejection. So in this graph, we're looking at the data that Brian had supplied us. His transformer is this ground to ground 1M, and that's this blue trace here. Obviously, what we're looking for is more rejection. So the green trace happens to be this transformer here. You can see it outperforms it over the entire frequency range. You can also see I made 2 more attempts. Here's transformer number 9 and 10. They perform fairly well, but you can see in this range right here, I don't know, about 150 kilohertz and 300 kilohertz, it doesn't perform quite as good as the Pico test unit does. So why not use this common mode transformer 8? You'd look at this and you'd say, woo, you know, that's probably the best transformer ever made. The problem that you run into, again, we talk about the return loss of the transformer. So here we are sweeping all the way up to 6 gigahertz. Again, this is the data that Brian provided us. And look at the return loss of our transformer. So it gets very poor. We're down at like minus 5.5 dB or so, 6 dB at 6 gigahertz. You know, compare that with about 2.5 dB or so for the Pico test transformer. You can see transformers 9 and 10 have a much better return loss, but again, the common mode performance for those 2 transformers isn't as good. So based on everything I learned making these first 10 transformers, I made 1 more attempt, and that's this transformer here. And again, that's comparing it with the data that Brian had provided us. And we can see now the common mode performance for this transformer is better than the Pico test transformer all the way up to 1 megahertz. And if we look at the return loss now, we can see it's much, much better. So a couple of things. Brian had collected data all the way up to 8 gigahertz, and I'm showing that here. And of course, I'm not able to run up quite that high. I'm collecting data all the way up to 6 gigahertz. And you can see how it flings off. This is just how AppCAD works when it reaches the end. But you'll notice one thing. See this ripple? That ripple is caused by a mismatch in the impedance of the transformer. That ripple is what allowed us also, though, to measure the length of the coax that they were using. So the length of coax in this particular transformer, it's quite a bit less than what's in this transformer. And to get the common mode up, I had to change the core material. So that's really the difference between these two. The other thing I'd like to point out of this document is the DC blocks. And again, I have a note here in red about how not to blow up your network analyzer doing these PDN measurements. Again, the DC blocks are available from PicoTest. It's a part number P2130A. These offer performance all the way between 500 Hertz and 8 gigahertz, and they have a 50 volt rating. This is looking at the frequency response with the HP3589A, and here you can see I'm sweeping between 10 Hertz and 150 megahertz, and I'm showing my 3 dB point at just under 200 Hertz. And you can see once we get up above about a kilohertz, the DC block is fairly flat. This looks like the software for the Nano, but it's not. It's actually, I run the same software on all of my network analyzers. So here it's attached to my Agilent PNA, and we're sweeping up to 6 gigahertz. Again, unfortunately, that network analyzer is limited on the low end to 300 kilohertz. But this is looking at S21 for the DC blocks I made, and we can see it's less than 1 dB a loss all the way up to 6 gigahertz. So what we're going to do next is just use this whole setup to run a very simple experiment. You can see we have the original NanoVNA. Port 1 connects to our DC block and goes to one side of our breadboard. The other side of the breadboard connects to a second DC block, which goes to one leg of our transformer. The other leg of the transformer comes out to another cable going to port 2. So again, it's basically what we've shown here. Of course, we don't really have any DUT installed right now other than our breadboard. So the first thing that we're going to do is calibrate this system. Let's go ahead and we'll select link, and then we'll select sweep, and we're going to change our start frequency to 10 kilohertz, and we're going to sweep to 1 megahertz. Next, we're going to select the transmission rectangular. We're going to change this to shunt through, and of course with the Nano we're only able to collect 101 data points. Now when I first started writing software for the Nano, I came up with the idea of doing segmented sweeps. So essentially what I'm doing is I'm basically have a little window of a certain frequency range, and I'm stepping that over the entire range that I'm interested in looking at, and that basically allows us to gather essentially as many data points as we want. Of course it takes a lot of time because each one of those segments takes about a second to run through, but again that's a linear sweep. Because the data for a PDN is going to be very feature rich at lower frequencies, really the ideal solution is to have a log sweep. Unfortunately, the Nano doesn't have that capability. So what I've done is I had created something called a quasi-log sweep, and the way that works is I essentially program discrete step points on a log scale, and I do that linearly across the range of interest. So it's not quite a log sweep, and it's not a linear sweep, it's a quasi-log sweep. So we do that by selecting the sweep mode. In this case you can see it's already selected to log, and then what we'll do is we define our start and stop frequency. So now when I select segmented sweeps, this is going to use 10 samples per decade to define that quasi-log, and it's going to sweep between 10 kilohertz and 1 megahertz. So let's just go ahead and we'll kick that off. Again, this takes a very long time to run. I'll go ahead and speed up the video so you don't have to wait for it. Once it's completed, it pops up this little dialog box, says it's done. Now what you can do is select sweep again, and it will kick off another trigger. We can also take this data now and store this as a reference point. So let's go ahead and do that. We'll just hit reference, and then we can do channel n minus reference. So that's going to normalize all the data that we collect going forward. So if we were to repeat the sweep right now, we're going to see essentially a line at 0 dB. So next what I'd like to do is insert our 100 microhenry choke, and again we're going to place that between the VCC and ground plane, and I'm going to repeat the sweep. But before we do that, let's select the Advanced tab, and now we'll select the Bode tab. This tab is specifically made for looking at the PDN. So we can view this data as raw S21. We can also look at it as dB ohms or in ohms. Off to the right you'll see something called target. This is the target impedance for the PDN that we're trying to measure. So for this example, let's say we wanted to design a PDN with a 10 ohm target impedance. So we just change this 50 to a 10, and let's look at this in ohms, and now we'll do a sweep. We can see for a target impedance at 10 ohms, the software is calculating that we need roughly a 1.225 microfarad capacitor, and that's going to be how we're going to compensate whatever the error of this PDN is. So the capacitance is going to be whatever our inductance is, in this case 100 microhenries, divided by whatever our target impedance is squared. So we're saying 10 ohms is our target impedance, 10 squared is 100. So 100 microhenries divided by 100 gives us 1 microfarad. So here we have a 1 microfarad capacitor. So what I'm going to do is place that in parallel with the inductor. Let's go ahead and save this trace to memory 1, and let's run another sweep. We expect that this should have a much flatter impedance, and it better be closer to 10 ohms. So let's see. Oh, it shot all the way up to about 26 ohms, and now it's coming back down. There's 5 ohms. Just turn off memory 1, just allow us to zoom in a little easier. Okay, it doesn't look very flat. It's gone all the way from 10 ohms basically up to about 28 ohms, and then down to essentially 0 ohms. So what's the problem? Well, the problem is we didn't consider the ESR of this capacitor. So when you're choosing capacitors to do the bypass, you have to make sure that the ESR is the same as whatever our target impedance is. Of course, that's going to be difficult to find, maybe some aluminum electrolytics. In this case, what we're going to do is we're going to add a 10 ohm series resistor with our capacitor. So again, this capacitor is in series with the 10 ohm, and that network is in parallel with our inductor. Let's go ahead and we'll save this to memory 2, and let's run a new sweep. And now we can see, compared to not having our series resistor, how flat this impedance is. This is really what we're after. Of course, a typical PDN network isn't going to look near this good. So here I have a piece of semi-rigid coax. What I'm going to do is just replace our breadboard with this, like so. And let's go back to the main menu. Let's go ahead and change our stop frequency to 50 megahertz. And what I'm going to do is clear out our reference. So now let's run a segmented sweep. Okay, there we have it. And we can again store that as our reference and select reference minus. And let's reattach our breadboard. And again, we'll go back to advanced and let's select ohms, and let's go ahead and select sweep. And again, across our breadboard we have the 100 microhenry choke in parallel with our 1 microfarad capacitor in series with our 10 ohm resistor. So a couple of things with this software: when we're running this particular mode, I only collect the data for port 1. So one thing about this particular mode is it runs a little faster. It's because it's not ping-ponging between the two data sets. So basically it cuts the time in half. Also, with it running a log sweep, we don't collect as many data points, so again, that helps speed this process up a little bit. Still takes a fair amount of time to run. You can see there are 3 different cursors. You can select cursor center, it brings them all to the center point. We want to look at this as S21 data. Here we have the phase as well as the gain. We can turn those off manually. We could select, for example, here to shut it off. We can turn all these graphs on and off, for example, if we want to turn off the phase. Or we can turn all the graphs on simultaneously. You can see what's happening once we got above 1 megahertz. Notice how the inductance is just going through the roof. Again, there's 35 ohms. We're almost all the way up to 50 ohms. So the impedance of this design is not very stable. Let's just go ahead and store that into memory 1. All we're going to do is replace our long leaded parts with these ones that I've cut off. Alright, so again, here's our 100 microhenry. Here's our 10 ohm resistor. And here's our 1 microfarad capacitor. Let's just see how this compares. If you like, we can change the color of this trace, so let's just go ahead and make this one red. See, it's fairly close. Maybe a little closer to 10 ohms than the other one. Could be part tolerances. You can see the impedance of our shorter leads is still remaining quite flat, but notice the previous data we collected with the longer lead parts starting to go up. There we have it. Let's go ahead and we'll save this to memory number 2. So now we can zoom into this area. Notice our impedance only got up to about 13.5 ohms all the way up to 50 megahertz just by cutting our lead lengths down. So that makes a huge difference. Of course, if we wanted to do even better, what I have here is the same circuit, and this is all obviously in surface mount. So for the inductor, I'm using these. These are a TDK part number NL322522T-101J-3. You can see 100 microhenry plus or minus 5%. Actually, this is a 20 ohm resistor. I've placed 2 of those in parallel to get my 10 ohms. I don't know if it'll show up on camera, but they are stacked on top of one another. And again, that was to minimize the package inductance. And again, we're just placing it between port 1 and port 2, just like our breadboard was. And now let's run another sweep. First thing you'll notice is that it comes right out of the gate at basically 10 ohms. You'll also notice that we don't see near the overshoot. There we have it. So again, let's go ahead and zoom into this area. You can see now the impedance is stable all the way up to 30 megahertz, and then between 30 and 50 megahertz it changes about a half an ohm is all. So again, I just want to point out that the packages that you choose for your PDN design will have a dramatic effect on how stable the impedance is. This is looking at our user's manual again, and here I'm showing a PDN that's a little bit more complex. Here's a 7805. You can see we have various bypass capacitors along the chain. There's also a oscillator, and then there's a little meter stuck across it. So you can see it's reading roughly 5 volts. And let me just show you what this looks like. So here we have both a powered off and powered on trace. This is looking at S21, and you can see there's quite a bit of difference in the impedance as we power this up. The lower frequency, we're looking at the electrolytics and of course the regulator itself. Up here we can see our oscillator. This is the 1.84 megahertz. Here's the harmonic of it. And we notice all these ripples. Each one of these is the bypass capacitors that we've got stuck across the chain. This is a lot more typical of what you'll find when you're looking at a PDN. And again, what we'd like to do is smooth out some of these peaks. Not just the high ones, but the low ones as well. All of these can cause the emissions problems. It can also cause other problems if you're working with high-speed digital. Obviously, any kind of noise on the power supply is going to cause phase noise in the digital signals or jitter. So far this demonstration has been about measuring higher impedances. And for most PDNs, the impedance is going to be quite a bit lower. So the question is really how low of an impedance can we measure with the Nano? So to help answer that, I had made up some different standards. Here we have two 50 milliohm resistors in parallel, giving us 25 milliohms. And then I have our 100 milliohm resistor that we used in this video. But I also have a 1 milliohm 50 ppm part, as well as a 100 microohm resistor. So in this table, what I'm showing you is the different resistor values. So here's our 100 milliohm down to 100 microohms. And I'm measuring these directly with the network analyzer. So for these measurements, the transformer is not being utilized. And we can see at 100 milliohms, I'm about 2.7% error. At 25 milliohms, we're at about 10.5%. At 1 milliohm, 216% error. And 100 microohms is giving us over 2,000% error. So then we've inserted transformer number 8. And now look at our error. We've gone from 2.7% down to 0.5. 10.5% down to 0.6%. 200% error dropped all the way down to 31%, and our over 2,000% error is now down to 183%. Of course, that's still not very good, so the question becomes is what really is the problem? And if you look at the circuit here, you could probably guess what the error is. So again, you've got the resistance of the trace, and we have the resistance of this solder where the resistor is added. And then we have the resistance of the trace on the backside. Of course, this is 50 ohms on the backside here. And because we're measuring on this side of our solder joint, we really don't know what the resistance of the standard is. So what we'd like to do is isolate this solder joint the best we can. And the way that I did that is I cut the trace, and then I allow the resistor to straddle that area. So essentially we've nullified the effects of these two resistors. The other thing that we've done is we've built up this area here in the ground plane. I couldn't just slice this in two, so I've added a whole lot of copper in this area to really minimize the resistance. So this is what our 1 milliohm resistor looks like now. See right here we can see the slice, and you can see I've taken solder braid and I've built this whole area of the ground plane up. So next I attach these two resistors to my bench power supply, and then I pump some current through them. I measured the current as well as the voltage drop across the resistors, and then I calculated the resistance. So for our 1 milliohm resistor, I measured 1.025 milliohms, and for 100 microohms, I measured 99.85 microohms. So here I'm attaching our 100 microohm resistor to my 3589A along with our transformer. So after the circuit board changes for our 25 milliohm resistor, we're now down below 0.5% of error. And now we can see for our 1 milliohm as well as our 100 microohm resistor, we're floating around 5% of error. So now that we have some idea of the tolerances of our 4 resistance standards, here you can see we have our 2 blocks installed. This is the 1 milliohm resistor, and here's our transformer. So the purple trace is our 100 milliohm. You can see it's right on the line all the way up to at least a megahertz. The pink trace is our 25 milliohms, and the green trace is our 1 milliohm. So if we zoom into this area, again 25 milliohms, it looks like it's pretty close. And again, this is our 100 milliohm resistor at top, and down here this is our 1 milliohm resistor. Let's just zoom into that area, maybe between 20 and 30 kilohertz. It probably is close to 1 milliohm. Now let's add our 100 microohm resistor to the mix. That's this green trace here, and you can see the Nano cannot discern between these two. The one thing we do see is the package itself is less inductive. In section 10.3, I talk about some of the common problems that people have reported. Most of these problems seem to stem from people not reading the documentation. One of the common things I find is that people will install the EXEs. Of course, that software needs the LabVIEW runtime engine, so then they'll go to National Instruments, they try to find the runtime engine for it. Eventually they may find one, and then they complain that it won't communicate with the device, and of course they failed to install the NIVSA as well. And again, this is the whole reason that there's that main installer. That includes the runtime engine as well as NIVSA. It also includes the INI file for the EXE. So all those things are important. Of course, if you want, you can install it by downloading the NIVSA and the runtime engine from National Instruments. But again, they are all included on the initial installer that's available up on Git. The next thing I run into is people will install the wrong software for their device. So they'll have, for example, the V2 Plus, and they'll try running the original software. Again, there's 2 programs for a reason. You have to actually grab the right one for your Nano for it to work. Another problem I run into is people will download the installer, so they get the runtime engine as well as the VISA, but then they assume that that 1.0 software is the latest and greatest. It's not. If you want to run the latest and greatest stuff, you have to download that separately. The only reason I left that original installer up there was, again, just to give you the initial setup. Once you have all the runtime engine and the VISA installed, then all you need to do is grab the executable, copy it over the old one, and you're good to go. This one came up recently again. Basically, people from outside of the United States will try using the software, and of course they have different regional settings. One of the common differences is where the comma is used instead of the decimal place for the separator. So, of course, what ends up happening, it's not a problem with my software, but LabVIEW will, of course, use the comma separator. It'll display all the variables that way. But when it tries to communicate with the external peripheral, of course, it's going to send down commas instead of periods. Most test equipment can't handle that. But that's not a problem, really, because you just modify the INI file. Again, that's in the documentation how to do that. In section 10.2 under Windows Regional Settings, we can see right here, you just modify the INI file to use the local decimal point and set that to false. Now, one of the problems, of course, is that you may not have the INI file. If you didn't actually use the installer, you won't have the INI file. So what you can do is just copy and paste this text. So this is the default INI file. This is created by LabVIEW when you run it the first time. And just create your own INI file. Copy this into the directory with the main program. Now, I talked to one person that basically said the only thing that they placed in their INI file was the use local decimal point equals false. And that worked fine as well. So you don't actually have to have all this other information in your INI file. The last problem that I run into is with people using unsupported hardware and firmware combinations. Now, that doesn't mean that this software will not work with different combinations. I'm just saying that I certainly haven't tested it. You may get mixed results. I don't know. I think it depends on what features you're really wanting this software for. So hopefully the video is giving you some idea what the new software's features are and how to go about using them. Again, if you're looking for more detail on PDN measurements, There's a lot of very good detailed videos on that subject. There's also a lot of papers that have been published on it. I suggest you just start doing some research in it. Well, I think that's going to be it for this video. I hope you enjoyed it, and maybe we'll see you on the next video. If you decide to run the software, good luck.